All right, guys. So on Tuesday we were talking about the sine, cosine, tangent functions and evaluating those. When we got to the end of class on Tuesday, we got to this chart, and what you're going to hear me say a lot in this class, there's going to be a lot of information in which you have a choice of whether you memorize it or you develop just a strict relationship that allows you to regenerate these ideas quickly. And it might take 10, 15 seconds to regenerate it, but I would think that time spent, 10 or 15 seconds, is better spent than trying to memorize something and my memory failing me and not knowing, or my memory messing me up and I transpose values. Does that make sense? So I would rather, in regards to that, experience a loss of 10 seconds than to be wrong because my memory was messed up. So in this picture here, we can do the idea, we can say that I'm going to memorize that the tangent and secant have these domains, and I'm going to remember that the cotangent and the cosecant have these domains. And that's fine, you can do that. But what I want you to understand is that if you know the sine and cosine, and we'll see another situation on this later on today as well, but if I know the sine and cosine, and the rules and relationships that exist between sine and cosine, I should always know what relationships exist or what characteristics exist for tangent, because it's simply the sine divided by the cosine. Does that make sense? I should know what the relationship is for secant, because it's just the reciprocal of cosine. I should know the relationship for cotangent, because it's just the reciprocal of tangent, or it's cosine over sine. And I should know the relationship for cosecant, because it's just 1 over sine. Does that make sense? So if I know sine's domain, I should be able to figure out tangents, or if I know sine and cosine's domain, I should be able to figure out tangent's domain. Now they say here that the tangent says its domain is all real numbers other than that is pi over 2 plus n pi, where n is just an integer. And this is where it's important. You heard me say in previous courses, maybe even in algebra, college algebra, that we need to know what our integers are, okay? Because I can't just let n be anything here. I can't let n be a half, because then that property doesn't exist when n is a half, right? N has to be a number like 0, 1, 2, 3, 4, 5, 6, 7, all the way to infinity, or they're opposites. Can't be a fractional part, okay? But what we're saying here, guys, is that if I know sine and cosine, all real numbers, I take the sine function, what they're saying here, and in your argument, remember the argument is the thing that goes in the parentheses, so I can go sine of whatever, that whatever right there, it means you can plug in anything that you want to, and you're going to get an output spit back to you, okay? So if I take my calculator, take sine, and close my eyes and hit a bunch of buttons, and then hit enter, okay, it's going to spit back a number to me, okay? It will never say undefined or domain error or anything like that, okay? And the reason for that, and remember, we've talked about on the unit circle, the sign on the unit circle, if that's just an arbitrary point, I take that arbitrary point and I rotate it all the way around, the sign is the y value, isn't it? Okay. Well, is the y value ever non-existent there? Does that kind of make sense? Is there ever, this unit circle, is it a complete circle? Are there any gaps or anything like that? No. So this point will always exist. So if that point is always going to exist, doesn't the y value always exist? Right? And saying something that's undefined is essentially saying it does not exist. Okay? So I'm always going to have a y value. Do I always have an x value? Yeah. Okay? So no matter what with that blue point, I'm always going to have an x value, I'm always going to have a y value, so I'm always going to have sine and cosine. I'll always be able to evaluate that and get an output back. Okay? Now these inputs are going to be either that arc length or the radian measurement that we want to talk about, or even if we're talking about degrees, it can be in degrees, but it's going to be always an output value that I get back. Now that output value that I get back, even though I can put any number I want to in here, I can put any angle measurement there, my y values are only going to be, what's the largest y value I would ever get back? 1. What's the smallest y value I'd ever get back? -1. Okay, so even though the domain is all real numbers, my range is stuck between -1 and +1. Okay, inclusive. I can get those ones back. Cosine's the same way. Now, how does that help me with tangent? Well, let's think about tangent. Tangent there says you have a domain restriction. It says that at pi/2 plus n pi, there's a domain problem. Okay. Well, think about this. This is the reason. This is why I think learning the relationship between sine, cosine, and tangent allows me not to have to memorize this sentence here. Okay. Because I know tangent of some angle, I'll just call it alpha, is equal to sine of that angle divided by cosine of that angle, right? Okay. Now, where would be the only time? So I've got division. Go back to college algebra, about the first, second week of college algebra. When I divide by what is that? What is that? What that provides me my biggest issue for domains? 0. So can I ask myself, where is cosine on the unit circle? 0. Anybody know? If I put my blue point right there, is that where cosine is going to have a 0 coordinate? Okay. And remember, cosine is the x-coordinate, right? So x is 0 there. So I got, essentially, I'd have sine of alpha there. So alpha is pi/2. Sine of that would be 1. Cosine of that would be 0. I get 1 divided by 0. What's 1 divided by 0? Undefined, okay? So that location there is pi/2, right? Let me move. My tablet's not working today, so I don't want to keep walking back and forth. So let me move my stuff up here real quick. All right, so pi/2 is going to be my first place that I have an issue with tangent. But doesn't cosine end up being 0 right there as well? Okay, so how far, if this was pi/2, how far is this arc right here that I'm tracing out? What is that length? It's just pi, right? Okay, so if I go pi/2 and I add to it pi, I get there. Well, what if I add pi again? Gets me back up here again, right? Add pi again, right? So I'm adding full values of pi. That's where this n pi comes from. Okay? If I want to add, obviously, when n is 1, it's going to get me to here. It's going to show me that other point on the unit circle inside 1 revolution that I have division by 0 for cosine, or cosine is 0. But if I add n to be 2, n to be 2 would take me all the way back around to there, right? If n was 4, it would take me 1 more cycle there. N was 6, it'd give me there, okay? And if n is, like I said, 3, it would get me to here. If n was 5, it would get me to here. So if my n's are odd, if my n's are odd, it would get me here. If my n's are even, it's going to get me there. Does that kind of make sense, everybody? Okay. So that's why I don't remember that. I don't memorize this. If you would have, before today, asked me what's the domain for the tangent function, I would sit real quick and say, okay, well, I know sine and cosine are these two things at pi/2, 3 pi/2, so then I could give you what the tangent is. Does that make sense? Okay. Secant's the same way. So secant is 1 divided by cosine, isn't it? That's what your secant is equal to. So am I still going to have division by 0 at the same exact locations of pi/2, 3 pi/2, and so forth all the way around as many times as I need to, so keep adding multiples of pi. Okay, so that's nice. And then cotangent, that's the reciprocal of tangent, right? If tangent was sine over cosine, then cotangent, being its reciprocal, would be cosine of alpha over sine of alpha, right? Or sine of my angle. So now I'm asking my question, well, where is sine 0, right? Well, sine's got to be 0 at what measurements? What angles? Okay, so 180 and either 0 or 360, right? If we're talking about degrees. So in terms of radians, it'd be 0 radians, pi radians, 2 pi radians, 3 pi radians, 4 pi radians, 5 pi radians, and so forth, right? And then you can see why this formula here exists. Whatever n is an integer, could be 0, could be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, all those different pi's that would provide me basically finding a coterminal point where my cursor is, there or there. Is that all right? So that's what I think is beneficial in learning a lot about sine and cosine. I think the relationships that tangent and sine over cosine and then these reciprocals are obviously important, and hopefully at this point we just know those. Those are hopefully common sense almost, and then that alleviates us having to memorize a lot of this stuff. Okay, I'm going to show you another chart here in a little bit. It's going to be this chart here. And now if you look at that chart when we get to this, there's a lot of like similar ideas or concepts existing from this one to that one, right? I'm starting with a sine of a negative angle, cosine of a negative angle. This one says I make the sine negative. This one says I keep the cosine positive. And those are easy to mess up. But if I can learn these two and understand those two and how those two come essentially from the unit circle, then these 4 don't need to be memorized. Okay? So we'll talk about that when we get there. Some examples, some things here. This graphic is just talking about the quadrants in which your trig functions are positive or negative. I think we've already got a better tool for this. A better tool for this would be that, right? All students take calculus. Okay. If you use all students take calculus, you have to remember that that is the device to tell you which trig ratios are positive. Does that make sense? And the way I remember that, what's the coordinate plane look like when I draw it with those red lines up there? It looks like a plus sign, doesn't it? Okay, so that's telling me which trig ratios are positive. And if I know which ones are positive, obviously I know which ones are negative. I think at the same time, if you learn this graphic here, you're going to mess stuff up because there's got to be, you got to put 12 objects over here. You got these objects here. You're going to mess that up. Okay. Remember, all students take calculus. You got that plus sign with the quadrants. Makes it so much easier. Okay. And those are little things, guys, that I think as you kind of progress through your education, obviously, a lot of your 11th graders, 12th graders, so hopefully you're already there, but you're going to be amazed by the little strategies that you kind of incorporate or take on and learn as you get into college level courses to remember things like this. It's essential. If you don't do that, you're gonna end up kind of hating stuff because you're just doing pure memorization. You're gonna, like I said in the past, that's gonna fail you. All right, let's zoom out a little bit real quick. All right, so these types of questions here, there are several different ways that we can approach these. Okay, first way, not the greatest, is to take the calculator, make sure it's in radian mode or degree mode, whichever one they're giving you, and just type it in, right? And that's going to give you a decimal. You don't have a calculator. There are very, very, very few calculators out there that I can type in cosine of 2 pi over 3, and it give me negative 1 over 2 as a fraction back. Or if I type in tangent of negative pi over 3, it gives me negative root 3 back. There are very, very few calculators that do that. It'll give me back the decimal approximation of those things, but it won't give it back to me in the exact format, right? With a lot of things that we do, we want the exact format, okay? Because that exact format with other algebra, one, it makes the other algebra, the future algebra, easier, but the conclusions of that future algebra come out to be like really, really, really nice numbers if we use the exact values of our sine, cosine, tangents. So that's one approach, use your calculator. And I do suggest using your calculator at the end to check to see if what you've done by hand or through the use of the unit circle is accurate. The other approach is to know this. So we got this point, 0 degrees or 0 radians, you get the order pair 1, 0. At pi over 6 or 30 degrees, you get root 3 over 2, 1/2. Pi over 4 is root 2 over 2. Root 2 over 2. Pi over 3 is 1/2 root 3 over 2. And pi over 2 is 0/1. All students take calculus. If I can remember that first quadrant, I think that's going to help us remember the second quadrant, third quadrant, and fourth quadrant. We talked about that the other day, right? When I gave you that handout for the unit circle. I think that's the bare minimum you need. Okay? If you're a person that wants to use the entire unit circle, you can use the entire unit circle. But that's more of a kind of having a cheat sheet in front of me and referencing that cheat sheet, and not really maybe necessarily learning the most efficient approach to doing these problems. So I'm going to do them both ways. I'm going to use just the first quadrant with reference angles, and then maybe go back to and just show you the unit circle and try this with the unit circle. Okay. So when it tells me cosine of 2 pi over 3, using this approach here with just the first quadrant, cosine of 2 pi over 3, what I like to do initially as you're learning this stuff, eventually you don't need to do this. Okay? You do this enough, you practice enough, you can visualize this, you can see this stuff in your head right away. But 2 pi over 3 is going to be in that quadrant because we know that this is 3 pi over 3, right? This is 0 pi. This here would be halfway between 0 and 3, right? It'd be 1.5 pi over 3. So that tells me that 2 pi over 3 has got to be a little bit further, right? So it tells me I'm in the second quadrant. Now the question is to find reference angles or reference distances. I'm talking about the arc length. It's that extra amount that I need to go to get to the x-axis, right? Well, if that terminated at 2 pi over 3, how much further, how bigger of an angle or how bigger of an arc do I need to get to 3 pi over 3? Pi over 3. So my reference angle is pi over 3, meaning that if I reflect across that line right there, that distance is going to go to right there, right? So this is that red point right there is the reference point that's going to tell me something about my blue point. Okay, they have the same coordinates, don't they? But one of them is positive, one of them is negative over here in the second quadrant. Okay, so pi over 3 is my reference angle. I'm going to come over there, find pi over 3. It's asking me for the cosine. What's the cosine of pi over 3? 1/2. It's the x value, right? Those are alphabetical, x comma y, c comma s. Okay, so 1/2 is my cosine, and that's what cosine of 2 pi over 3. That's the same exact quantity. Okay, but cosine for 2 pi over 3, 2 pi over 3 is in what quadrant? The second quadrant. And sine is the only thing that's positive in the second quadrant, right? So when I'm evaluating cosine, it has to be negative. And think about that. If I wanted to go from 0, 0 to that point right there, which direction do I have to move first? Left. So the x value of that ordered pair has to be negative because of that movement to the left first, right? Now, what I suggest is to take your calculator, change it to radian mode, type in cosine 2 pi over 3, and it's going to spit back negative 0.5 to you. So that's confirming that the logic you went through in producing that negative 1/2 of the unit circle was accurate. Does that make sense? Okay. Now, that should be eventually something that we incorporate into our work that we do very, very quickly, very, very efficiently. Okay. You could be a person that does this. Here's my unit circle. I'm going to go find 2 pi over 3. Okay, it's right there. They said cosine, it's the x value. And I get my negative 1/2. Does that make sense? Okay. But if I'm going to do that, say I want to do that for 11 pi over 6. Well, I need to have this chart, this entire chart in front of me every single time, right? And that's just not realistic. That's not something that we're going to do, okay, or have. So if you're a person that wants to do that, that's fine. There will be some quizzes and tests that I give you the opportunity to use either the entire unit circle or part of the unit circle, but at the same time there's going to be tests and quizzes where I take that away from you because I want you to go from what you know and not what your resources or learning devices are showing you. Does that make sense? Tangent of negative pi over 3. So we'll do that one. Tangent of negative pi over 3. when the angle is negative, there's several approaches you can use here. Okay, let's just approach it directly with the negative pi over 3. So negative pi over 3 just tells me I'm going that direction, right? And I would get to that second red point there. Because again, pi over 3 is less than pi over 2, correct? Okay, so this mark here would be negative pi over 2. So negative pi over 3 is got to stop short of that. Okay. Now the question is reference angles. If I'm thinking about reference angles, how far do I need to go to get back to the x-axis? Well, it'd be retracing the distance that I already traveled, right? Or the angle that I've already traveled. So how far would be my reference angle? Pi over 3. So tangent of negative pi over 3 is going to be the same thing as tangent of pi over 3, except for the plus or minus aspect, right? Okay. So pi over 3 is what I'm going to reference. Okay. If I'm looking at my unit circle, pi over 3 has the order pair 1/2 root 3 over 2, right? And that is my cosine comma my sine, right? There's no tangent on there. But what's the relationship between knowing those two things and learning what my tangent is? Okay, good. Tangent is sine over cosine. So tangent of negative pi over 3 should be the same thing as sine divided by, sine of negative pi over 3 divided by cosine of negative pi over 3, right? Make sense, everybody? Now, because we're using pi over 3 as my reference angle, I'm going to take radical 3 over 2 as my y value. That's my sine. This is my cosine, so 1/2. What are those going to evaluate to? Radical 3. So those 2's cancel out, right? Just leaves me radical 3 over 1. So we get radical 3. Okay. So that's the tangent of negative pi over 3. The value is radical 3. But negative pi over 3 is in what quadrant? Fourth quadrant. Okay. So when I did this division, all students take calculus. Cosine is the only one that's positive, right? So this sine should have actually been a negative there. This cosine is a positive. What's a negative out of a positive? Negative. So negative root 3 is actually what I'm looking for. Okay? And that's confirmed by knowing that all students take calculus. Cosine is the only one in the fourth quadrant that's positive. So tangent, the one I'm looking for, should be negative. Does that make sense? Okay. Now, is that the only way I could do it? No. Some people don't like using negative angle measurements. Okay. And this is what we learned. This was like the first day of class in regards to trig that we talked about this. If I take tangent of negative pi over 3, is that going to be the exact same thing as tangent of negative pi over 3 plus 2 pi? Yeah, if I add 2 pi to it, just gets me back to a coterminal spot, right? When I add 2 pi, that's going to evaluate to a positive angle. This gives me tangent. So that 2 pi is 6 pi over 3. So this will give me 5 pi over 3, right? Okay. So now I can think about this. Okay, 5 pi over 3. Well, again, the idea here is that this would be 3 pi over 3. This would be 6 pi over 3. This would be 4.5 pi over 3. So 5 pi over 3 is telling me I'm going a little bit further, right? Okay. So I'd be looking for what reference number? What would that distance right there be? Pi over 3, right? So I'm going to reference pi over 3 again, which is the same reference of pi over 3 that I used when tangent was negative, right? Negative pi over 3 is the first angle. So that's an option, okay? And you would go find, okay, well, tangent of 5 pi over 3 is the sine of 5 pi over 3 divided by cosine of 5 pi over 3. You can go that route. If you're a person who wants to use unit circle, here's my 5 pi over 3, right? There's my sine value. There's my cosine value. If I divide them, do I get negative root 3 right off the bat? Yep. Okay. Using the complete circle like this, guys, obviously it's a little bit easier in evaluating because the sines, the SIGNs, are already there, right? Okay. If I'm just going to use the first quadrant in reference angles, which is what I'm hoping we do. I'm going to suggest and try to urge you to use that technique because it's less memorization. You have to be able to understand what quadrant you're in so that you get the correct plus or minus. And that's usually, that's one of the things that I'll give an assignment, web assign, test, or quiz. And the answer is negative root 3. Somebody has root 3, and they say, oh, well, I must have just forgot the negative sign. Well, yeah, you either just forgot the negative sign or you completely don't understand what we're doing. Does that make sense? So I can't take that argument anymore and say, yeah, it's just a detail that you overlooked, because it's not now. Okay, this is a big issue if I don't have that negative for that root 3. That last one, sine of 19 pi over 4, same concept. Sine of 19 pi over 4, is that more than one revolution around the circle? Yeah, so when I see my denominators, guys, I automatically take my unit circle, and instead of writing it in terms of like 2 pi and pi, I automatically write 2 pi and visualize it as 8 pi over 4, and this would be 4 pi over 4, right? Okay, that'd be 2 pi over 4 and 6 pi over 4. So I think about it that way. And now if I look at the 19, well, that's more than 8, right? Okay, so that's at least one revolution. But 19 is more than 16, isn't it? So it's actually more than 2 revolutions. So you can visualize this. So 19 pi over 4, there would be 8 pi over 4, 16 pi over 4. I need to go 3 pi over 4 more, right? Well, there's 2 pi over 4 more, and there would be the third one, right? So that's kind of, if we're thinking about an arc length, now obviously the way I drew it is so you can see the rotations, but essentially the arc length would be, more than 2 1/4 ways around that circle. But if I'm talking about the angle measurement, okay, it is much larger than 360 degrees or 2 pi, something like that. Does that make sense? You can do it this way. It resides right there. It's coterminal with what would end up being 3 pi over 4. And you can pick off that value off the unit circle. But what I think is easier, once you recognize, guys, that number right there is more than one revolution around. It'd be the same concept that we did here. There we added 2 pi, right, to get something between 0 and 2 pi. Here, we're going to take 19 pi over 4, and we're going to subtract 2 pi. That gets me 11 pi over 4, right? But that tells me 11 pi over 4. That's still more than one revolution around. So I'm going to subtract another multiple of 2 pi. And I keep doing that until basically my numerator, when I subtract the 8 and the 8, that numerator is a number between 0 and 8, right, in this case? So what's 19 minus 8 minus 8? 3, right? So this thing is equivalent to sine of 3 pi over 4. Okay? Well, sine of 3 pi over 4, using this picture again, 3 pi over 4 is going to be right there, right? We said this is 2 pi over 4, and that's 4 pi over 4, so we got to be halfway there, right? Halfway between those two. What would be this additional amount, whether it be an angle or an arc, what would that additional radian be to get to the x-axis? Pi over 4. So my reference number, t bar or theta bar, is pi over 4. So sine of 3 pi over 4 is going to have the exact same value as pi over 4. So if I think about pi over 4, reference to the first quadrant, pi over 4, right here in the first quadrant, radical 2 over 2, radical 2 over 2, right? So sine there is radical 2 over 2. Okay, that's nice. But we were dealing with 3 pi over 4. And the sine of 3 pi over 4, is that positive or negative in the second quadrant? Sine is positive. So we're good, right? Radical 2 over 2 should be that result. Now, talking through all that stuff, it takes some time to do each question, right? The hope is that when we're doing this on our own, okay, it's almost an instantaneous thing that we visualize that and we can recall those values pretty quickly, okay? Obviously, if you are a person that's going to use the complete unit circle, okay, 19 pi over 4 doesn't exist there, right? So you still have to incorporate the coterminal angle aspect to reduce that to 3 pi over 4. And then if you want to pick off the radical 2 over 2 from that picture, then you can. Okay. Questions on that? That's something we can do? All right. Now, there are some things, guys, that are going to allow us to kind of expedite the all students take calculus thing with negative angles or positive angles, depending on which ones we're interested in. And it's this concept right here. Actually, before we get to that, let's actually look at these real quick. These types of questions, guys, these are, I hesitate to even talk about them, but they're kind of goofy because the only thing we have to do is take our calculator. If they want to find 2.2, 2.2 is in the second quadrant. Okay, that arc length is greater than 1.57 is pi over 2. So 2.2 is going to be in the second quadrant. The sign value is going to be positive, right? Basically, all I've got to do here, because it's not one of the 17 points off our unit circle that we've memorized or that we can use reference angles for, that one we have to grab our calculator and type it in. Does that make sense? Okay. So if you're not getting multiples of pi over 6 or pi over 4 as your inputs for your sine, cosine, tangent, secant, cosecant, cotangent, you have to grab your calculator and type it in on your calculator. Now, the number one error I get is that people see 2.2. Oh, that's got to be a degree. Is there a degree symbol there? No. So you infer that they're talking about radians. Okay. Now, let's think about what that means to us. If I were to take the cosine of 2.2, it gives me back that value right there. If I were to take the sine of 2.2, it gives me back that value right there. I think I can do this. Control C, V, comma, Control C, V. I'm going to place that point right there. Does that make sense? Well, why is that point important to us? If I go x squared plus y squared equals 1, is that point on that circle? On the unit circle, right? Okay. So 2.2 radians would be the arc that goes from here all the way up to that black point. Okay. Another thing I can do here is the idea that if this is true, if that point is on the unit circle, then I should be able to take this value. Let me just kind of cut and paste all of this to make it a little bit easier real quick. I should be able to take that value, the x value, and square it, add to it the y value, and square it. And what should I get when I square this? I should get 1, right? Okay. So it's telling me information that I can use to verify that I do indeed have that 1. Now, think about the unit circle. The nice thing about the unit circle is that I could actually take cosine of anything, square it, add to it, the sine, I don't know what just happened there. There we go. The sine of anything, and square it. Okay, so add a slider. Yes, I want to add a slider. So it gives me this, right? Well, cosine of A is kind of like putting in this number right here. It's negative 0.588. And sine of A will then be putting in the 0.808 that was associated with the same 2.2, right? Well, if I do that, but I let A be anything, and I start moving this A value, what do you see that happens with that value right there of 1? Stays the same, right? This is what we call an identity. No matter what I plug in there, I'm going to get the same result back. Okay? I get a statement. No matter what my input is, I get a true statement back. Okay? Now, if, for instance, if I was a 3, see how it's no longer an identity? I'm getting different results back when I cube that. Okay? But when it's squared, we do have that identity. And that's a very, very essential identity for what we do in this course. That's all because of that circle, that unit circle. Think about the unit circle. X squared plus y squared equals 1, right? But what have we said the x always is? The x is your cosine, right? Can I make that substitution? Okay, so let me kind of draw that for you real quick. All right, so we got our unit circle here. We have said that every one of these points here is the x value, comma, y value. The x value is a cosine. The y value is a sine, right? Well, if I'm so those things relate. If I'm on the unit circle, I know this unit circle is made by the algebraic equation x squared plus y squared equals 1, right? Well, we just now said x is cosine, right? So can I make that substitution? Say cosine squared. My y is sine, so say sine squared is equal to 1. Now, in each one of these, we would have whatever our argument, so some theta maybe. Okay, so that you're going to see x squared plus y squared equals 1. We know that's hopefully something that's been drilled into us since maybe geometry, but now, because x is cosine and y is sine, it generates that new formula, and we call that a Pythagorean identity, because the Pythagorean theorem does exist. There's a right triangle up there and all that kind of stuff. And that cosine squared plus sine squared equals 1 is going to be very, very useful to us. Okay? Those other ones, obviously, then, typing. I don't have a cotangent button on my TIA 304, so I go 1 over tangent of 28, right? If you're dealing with Desmos or GeoGebra, you can just type in COT. All right, so this gives me what we call even and odd properties. Okay, and these are based off of just symmetry from the unit circle. There's 6 of them up there, right? All 6 of them look very similar, right? I want us to focus on learning 2 of them, and then once I learn those 2, I know all the others. So I want to focus on just learning these 2 right now. Okay? And the idea here, guys, is if I were to pull up so they're saying sine of negative t. Let's do it this way. It's a little bit easier, I think, this way than what I did in the last class. The identity says the sine of the opposite of t is equal to negative sine of positive t. Okay? Well, what does that mean? Well, if I take sine of negative t would be going that direction, right? Now, I can pick off any one of these angles that I want to, from 0 all the way up to negative 2 pi. But let's just say I'm going to look at negative 5 pi over 3. Sine of negative 5 pi over 3. And it's negative root 3 over 2, right? Okay. Well, is that going to be the same thing? So sine of negative 5 pi over 3. Is that equivalent to saying sine of 5 pi over 3, but multiplied by a negative 1? I'm sorry. Yeah, that's fine. So my apologies. Negative 5 pi over, this is not negative 5 pi over 3, is it? That is negative 5 pi over 3. Okay. Is that going to be the same exact, so sine of negative 5 pi over 3, which is radical 3 over 2, is that the same thing as the sine of 5 pi over 3? So the sine of 5 pi over 3 would be this point, okay? Or is that value right there and that value right there are the same amount but opposite signs? So that's all this identity is saying, okay? If I want to find sine of negative t, it is the same thing as sine of t, just negate it. Does that make sense? All right, now, the reason that exists is if I were to take this point right here and reflect it across the x-axis, it would turn into that one, right? And then reflect it across the y-axis, it turns it into that one. Do you guys remember back to college algebra what a function was called if it was symmetric about the x-axis and the y-axis? It was odd. That was the word for, and basically the way I remember this is reflective across the x-axis and y-axis is origin symmetry. Okay, it's analogous to that. And odd starts with O, origin starts with O, right? Okay, so anything that's reflective across the x-axis and followed up by the y-axis is called an odd function. That's why this is an odd relationship. Does that make sense? Okay, it has nothing to do with like 1, 3, 5, those kinds of odd numbers. It's the symmetry relationship. Okay, even ones are just symmetric about the y-axis. Okay, so we see those here in a little bit. All right, so let's talk about cosine of negative t, cosine of t. If I say I want to find the cosine of negative, let's just say pi over 4. That would be right there, right? Cosine of that, so that point is going to be radical 2 over 2, comma, negative radical 2 over 2, right? So there's the cosine of it. This rule right here, this odd and even property, is saying that it should be simply the same as just cosine of pi over 4. Or, yeah, cosine of pi over 4. So all I have to do is essentially drop that negative. Cosines, they're the same exact thing. Cosine negative pi over 4 is exactly the same thing as cosine pi over 4. Why is that the case? I'm going from, remember, cosine is just an x value, right? I'm going from 0 to 0, and I want to get to that point. Do I travel that x distance first? If I'm going to that red point, do I travel the exact same x distance? Yeah. Okay. So if this one was positive, that one's positive. Okay. Now, so those are two. Hopefully that explanation makes you understand them. Right now, if you don't understand that relationship, at least memorize those, and then we're going to use them. And hopefully through the next couple of days, couple times we use them, eventually that relationship kind of surfaces and you kind of understand it. But now, why would I only need those two to figure out tangent? Think about this. Tangent of the opposite of t would be equal to sine of the opposite of t over cosine of opposite of t, right? That make sense? Well, what do we say sine of opposite of t was? Negative sine over t. So let's put that, because look at this. What tangent is, it's getting rid of the negative angle, right? And it's going to produce a positive. So somehow, I need to get rid of that negative angle, I need to get rid of that negative angle. They can't show up. Cosine of negative t, we just talked about as being just the same thing as cosine of t, right? Now, when I take sine of t divided by cosine of t, what's sine of t divided by cosine of t? Yep, go back to tangent, and it'd be tangent of t, right? But it was negative divided by a positive, so this is going to be negative. So do you see how I can go from that to that without having to memorize it, right? Just knowing my relationships with sine and cosine. And my hopes are, guys, that, and it does happen. I know right now it's the first time you saw it, so it takes some time and some thought. But the more we go through this stuff throughout the next 13 weeks, that stuff's going to be almost instinctual. It's, tangent of negative t, yeah, it's obviously negative tangent t, okay? Because of how much we use it and how beneficial it is to us. Through the problems that we do, you're going to be forced to have to learn that stuff, okay? Does that help? Tomorrow, so that's all just kind of understanding relationships on the unit circle and the order pairs on the unit circle. Tomorrow we're going to do those questions that are like write tangent in terms of sine or write secant in terms of tangent, okay? Because those things are going to allow us to do some algebra later that's a little bit easier, okay? Do solving some equations that are a little bit easier. Maybe I have an equation that has tangent in it. It's easier if I can get rid of the tangent and put sine and cosine in. So we'll do that tomorrow. And these things might show up in some of that stuff. It's called identity work. That's kind of where we're going to go. Hopefully wrap up section 6.2 tomorrow. I did open that back up. It's like due on Monday now. And I gave you 2 more similar exercises on that if you rushed. I did say the other day that I wasn't going to, even though I didn't change it, but it was not going to be due today. I'm going to postpone the unit circle quiz till next week as well. Okay, so earliest obviously will be Monday. So make sure you please. Last class told me about 2/3 of them told me, yeah, I already know it. Okay, so you can give it to me today. The other third was kind of hesitant. So at least know that by Monday.